Hi, everybody. I'm Anuradha Chandrasekaran. I'm here to present on synthetic data and its application in health professions research. I work with TTOHSC, School of Health Professions Educational Technology. We're here to start with a problem, right? In educational research, one of the problems that we come across is, can we predict students at risk? And considering our data has more than 90% say of Bs and hypothetically say 8% get As and Cs are very rare, how can we predict these students at risk? We have a very high class imbalance. We have a class imbalance problem essentially, which is veering towards the majority class and kind of glossing over the minority data points. And how do we ensure privacy? How do we ensure student privacy? How do we ensure data quality so we can get accurate predictions? How do we get accurate predictions based on minority underrepresented data points? So that is our problem here. And so also the issues that we see quite often in data that we come across is insufficient data, right? Like the number of Cs, very rare. We have a few records. Or poor quality of data. We have, say, missing information in healthcare data. Lots of fields could be missing data and or unlabeled data. So you have thousands and thousands and thousands of records with information, but they're not categorized, unlabeled data. And it could have inherent bias, which again is about the majority, the majorly represented data points, or it's going to veer towards that in terms of predictions. And the minority sample points are not going to be represented in the modeling algorithm. And privacy issues, right? So we have student privacy and patient privacy. All of these things could could happen. And one of the things that could help us resolve these issues is synthetic data. And what is synthetic data? Synthetic data, as the name implies, is essentially artificially generated. It's artificially generated from real data, but it has the same statistical properties as real data, and it's generated by computer algorithms, some of the modeling algorithms that you might have heard, undersampling, oversampling, SMOT, and all that. And we'll look at that in just a little bit. And it's obtained by creating a model that captures the properties, the statistical properties. So we're talking distribution, correlation between variables, all of that. So you capture all of that, you keep the same statistical properties, but it's generated by computer algorithms. And so what could be the benefits, right? And the benefits could augment existing data sets. So you have a data set, you have severely underrepresented data points, and this could help augment those. And we could generate anonymized data so we don't have to worry about student privacy and patient privacy. It could help mitigate algorithmic bias in AI models by ensuring that the AI model has more exposure to such underrepresented groups, right? Like we just saw, number of Cs are very rare. It'll be highly underrepresented. So now if we could augment that, the model has more exposure when we do classification, random forest and all that. The model has more exposure to such underrepresented groups in the training phase, and hence we can mitigate algorithmic bias towards them. So application in healthcare and education. In healthcare, we are able to use this because now we can reflect the original distribution of the data instead of revealing actual patient data, which again would help reduce the regulatory barriers because now we can actually share the data among multiple organizations because we're not using real data. And this can go towards improving our public health models because now when we share, we have more data towards predicting and towards more accuracy of our healthcare models. And this also could help in education because now we can model effects of teaching strategies without compromising student privacy. So you might ask me, we already have de-identification techniques like sampling, encrypting, masking, all of that, deleting columns, removing first names, last names, all of those protected information, right? So why do I care about synthetic data? Researchers have recently been able to create a model where 99.98% of Americans would be correctly re-identified in any data set using just 15 demographic attributes, just 15, that's 15 columns. Now, how many columns, how many attributes do we look at data in terms of healthcare and education? There's hundreds of attributes, right? We only need 15 to re-identify people. So that's the problem with de-identification techniques. Now, synthetic data, we're not obscuring the underlying data, we're creating an entirely new data set based on the real data, but you're still retaining its statistical properties. That's the advantage of that. And here are the algorithms that could help create those. So we have random oversampling, random undersampling, SMOTE, which is synthetic minority oversampling technique, and ROS and RUS are basically, they use the existing data, and but SMOTE is different because it's creating a new data, it's creating a new data point around the minority data points using k-nearest neighbor algorithms. That's the difference between oversampling, undersampling, and SMOTE. Because oversampling, undersampling, you're still working with the same data set. And borderline SMOTE is where you only create these data points between the majority and the minority borderlines. So that way you're not introducing noise in the data. Safe level SMOTE is another algorithmic variation of SMOTE. And then ADASYN is adaptive synthetic sampling. Clustering-based algorithms, we create clusters and then use a technique like SMOTE. GAN is generative adversarial network, which is a machine learning algorithm that is used in generative AI. And I applied these algorithms on Iris dataset. So Iris dataset is just, it's available out there, public dataset, and I just ran SMOTE, ROS, and RUS on it. And here's the results of that. So in this one here, I have a box plot of the original data. And here I have the SMOTE applied, and here I have the ROS applied, and here I have the RUS applied. So you can kind of see the majority and the minority data points. The majority are shown in red, and the minority data points are shown in blue. So you can see that in SMOTE, we've increased the number of minority data points. Using ROS, again, we've increased the number of minority data points. And but using RUS, we've decreased the number of majority data points. We've taken them out to address the data imbalance scenario. And here we can also see histograms of each, right? So using petal length, we can look at the histogram across all of those. So original data, SMOTE, ROS, and RUS. And we can see that the density has changed based on the application of the algorithms, but the shape of the histograms are the same. I also went ahead and applied correlations between petal length and petal width across all of those different data sets. And you can see that original data set had a correlation between length and width as 0.96. And after we apply SMOTE, it's 0.97. After ROS, it's 0.97. After RUS, it's 0.97. So it keeps it around the same spot. And I also ran some summaries, which looked at quantiles and the mean, median, variance. So you can see that they are pretty much the same. We can see it. The median is slightly different because of the addition and removal of data points. But the mean, you can see, is pretty much around the same. The variance, you can see, is pretty much around the same. The standard deviation, it's kept pretty much around the same. And we can see the change, the kurtosis is pretty much the same. But the skewness, you can see a slight difference because they added data points. There are algorithms like borderline SMOTE, which address skewness a little bit, which still keeps that if that is needed for the model performance. Moving on, we have a study where they've used breast cancer data set, so highly imbalanced breast cancer data set. How do we have better accuracy in detecting breast cancer in highly imbalanced data set? So they've done this comparison study using several different oversampling techniques and their usual classification models. So they take the data, they do the data pre-processing, and then they've gone through training, testing, and validation. They've kind of separated them out. Once they've done that, they are sending it directly to the classification models like logistic regression, naive Bayes, and SVM, and k-nearest neighbor, decision trees, random forest, all of those things. So they're doing that. But then another way of doing it, they're also sending it through oversampling techniques like we just saw, random oversampling, SMOTE, borderline SMOTE, SVM SMOTE, all of that. They're trying all of that and then sending it to the classifiers. They found out that logistic regression has the highest accuracy after using any oversampling methodology. So that's one of the things that found out. And then followed by SVM with 90% using, so SVM SMOTE. So they use SVM SMOTE first and then send it to SVM classifier. And in conclusion, they're also saying the majority of oversampling techniques actually improve the diagnostic efficacy of the models. So they're useful in increasing the efficacy of the models, especially in a scenario where you have high class imbalance. And here you have all of the references that are used in the paper, so feel free to look at it. I hope this really helps in your research, in your healthcare or educational research. And if you have any questions, please feel free to reach out to me. My name is Anuradha Chandrasekaran. Again, thank you for giving me the opportunity. Thank you.